Have you, like me, ever looked out your window and wondered why the universe was the way it was? As you watched clouds float by or stars twinkle in the night sky, did you stop to consider why we live in a universe that looks quite the way it does? All great truths are simple in final analysis and easily understood. If they are not great truths, so said Napoleon Hill in his book, The Law of Success. And when it comes to the universe, I believe that is right. There have been many complicated mathematical formulas over the years that have attempted to map out the universe, but when great breakthroughs have happened and our understanding of the universe has been advanced, it has often been through equations and explanations that are incredibly simple. F equals ma, E equals mc squared. These are succinct enough to be explained in just a few lines of text or a few algebraic characters. But more than just the clouds, what are the great truths that underpin the universe itself? What is time? Why does the universe look the way it does, constantly expanding in all directions from everywhere? Why does light have a speed limit? I'm Alex McColgan and you're watching Astrum. And if you have ever wondered these same sorts of questions, perhaps the models in this video that I've developed with my brother might help explain the answers. Ultimately, a great truth must be simple. The ideas here likely still need development, but I believe that they explain the subject in a simple enough manner that they might just be the starting point we need to find the truth. To begin, let's start with a fundamental question. What is time? In this channel, we've talked a lot about time. As black holes warp space around them, we've learned that time slows down. We've discovered the time-influencing effects of gravity and even how the James Webb Telescope can peer through time to the distant past by taking advantage of the fixed speed of light. All this makes sense so far, but what actually is time? You can't taste it, touch it, or feel it, yet time has an unstoppable influence on us and is pushing us forward whether we like it or not. Doesn't something that impacts everything we do deserve some additional understanding? Thanks to this first model, we are going to have a possible explanation for why time slows down as velocity increases, and why shapes warp when undergoing velocities close to the speed of light. This model is based on recognized scientific theory, where we have taken scientific concepts and combined them into something you may not have seen before. But before we get to that, we have to begin with one foundational idea. Time is actually another dimension. Now, before you double check that you haven't logged into some sci-fi channel by mistake, let's discuss what I mean by dimensions. While in popular culture, different dimensions are often described as parallel worlds that are very similar to ours, yet subtly different. In this context, when we talk of different dimensions, we are referring to the dimensions of space, as in three-dimensional space, or 3D space, which may be far more familiar to you. This is by no means trivial though. 3D space is all around you. It is the around you, and is very relevant to our topic. Let's begin by making sure we understand the 3Ds and the relationships between them before we add the fourth D. Broadly speaking, 3D or three-dimensional space simply refers to space that can be measured in three different perpendicular directions. The perpendicular nature of these dimensions is important, but we'll get to that later. Three-dimensional space is usually described as having height, width, and depth, and they all have 90-degree angles between them. Simply put, objects like us that exist in 3D space can move left and right, up and down, and forwards and backwards. We are comfortable with this kind of space. Using this as our basis, it becomes much easier to imagine what we mean by 2D space and even 1D space. To move from one space to another, all we need to do is remove or add an extra dimension of measurement or movement that must be a 90-degree angle from all previously existing angles. So, 2D objects move in a plane that's bounded by the x and y directions, or the x and z directions, or the y and z directions, but not all three at once. 1D objects can only move either along x or y or z. Imagine a person who lived in such a 1D world. Their whole existence would be found either moving one way or the other. All of reality would exist either to the left or to the right of them, and would appear as a singular dot. They could not move or see in any of the other directions, and probably could not even comprehend such directions as even existing. Photons whizzing by them would only be visible if they entered the singular line that was a 1D person's whole area of existence. Now, adding extra directions of movement is what's needed to move things up from 1D to 2D to 3D. So, in theory, we can predict what we need to do if we were to jump to 4D. However, here we hit a snag. While it's easy to draw a line that's perfectly perpendicular to a single other line, or to draw another line on top of those lines that is perpendicular to the two previous lines, how would we draw a fourth line that's perpendicular to all three? Surely such a thing is impossible. Well, within 3D space, such a thing is impossible. The best we can do is draw approximations. For instance, it's possible to draw an approximation of a 3D shape on 2D paper by doing something like this. These lines are all two-dimensional, but we look at this and our brain recognizes that this is a picture of a 3D shape. So, in the same way, we could probably do something similar to what a 4D object might look like using just 3D lines. Mathematicians have attempted to do this, although their results tend to be a little confusing. Although this is mathematically sound as a basis for a 4D object, I personally don't find my understanding of 4D space deepened by looking at it, so I won't focus on it in this video. There is some evidence, however, that a fourth direction exists, and we are moving along it right now. That fourth direction, or dimension, is time. Einstein predicted this connection when he linked space and time into one unified space-time in his theories of relativity. According to him, time and space are two parts of the same thing. To me, this connects with 4D space very nicely. Just as there is no real difference between the Z and the X or Y directions, so too would there not be any difference between time and space if time is just another direction, albeit one that we can't see. And time is important. Without time, our 3D space wouldn't move. It would perpetually be in one state, because it's time that allows us to move about in it. But why can't we see it? Why can't we look in the direction of time? To explain this, let's look at the difference between the different dimensional spaces. We best notice this when we consider what 2D objects might look like if they were to move around in 3D space. This is where we start to delve into the model. Let's begin by visualizing a standard 3D space. But because we want to eventually see all of space and time in one model, let's cheat a little. Let's compress all of 3D reality as we know it into a flat, two-dimensional place. In this plane, let's make that our XY plane, which we will label space, which frees up the Z dimension for time. In this model, all 3D people are now just 2D. A 2D person could exist and live their lives in the place marked space at the bottom of our chart. However, by moving them up on the chart at a constant rate, they are also moving through time. Let's for ease and convenience say that the top of our diagram is the future, while the bottom is the past. So the higher up our 2D person goes in this diagram, the older they get. As we don't seem to have a whole lot of control over our ability to travel through time, let's imagine for a second that our 2D person travels upwards at a constant rate, as if there is some consistent force or wind at play pushing them upwards towards the future. Sadly, we cannot slow down time for ourselves simply through willpower, no matter how much we might want to do so. However, it is misleading to say that we can't change it at all. The faster we travel in space, the slower we travel in time. This is one of the guiding principles of Einstein's relativity. This model can express this idea through the power of vectors. As our 2D person tries to move to their left or to their right, their vector of travel changes. While traveling at a fixed rate, like a sail on a ship catching a breeze, we can only go as fast as the wind takes us, so the vector coming out from their front must always remain the same. To travel the fastest through time, our 2D person must orient his vector completely in the future direction or upwards. However, if they are to travel any amount in either direction to their sides, they can only do so by pointing their vector away from their direction of travel. They have motion in the x direction now, but they have done so by reducing their motion in the z direction. They are moving through space, but at the cost of moving a little slower through time. Taking this to its furthest extreme, our individual has completely flipped on their side and now only has motion in the direction of x and none in the direction of z. They have velocity in space, but not time. So I suppose this implies our vector is the speed of causality, or the speed of light. If this is the speed we're talking about, then moving at low speeds through space would not have any noticeable difference in our speed through time. We'd have to go really fast before we started to notice anything. The vector still mostly points upwards. An interesting result of this model is that, from the 2D man's perspective, nothing has really changed. He has his own view of what reality is. For him, the vector coming out of his chest is still time. The dimensions of the plane he's lying flat on is his space. To him, it's the rest of the universe that's gone a little weird, but he himself is perfectly normal. However, once he reorients himself, it is clear that the rest of the universe has moved on without him. This is clearer if we add a second 2D person. Initially, both of our individuals do not move in space. All of their vector is pointing in the direction of time. Nothing that strange seems to happen so far. However, if our stick man on the right turns and vectors at near the speed of light for a bit, then reorients himself, while the second 2D man on the left just stays where he is, it becomes clear that our 2D men have not moved at the same rate through time. Assuming that our two stick men can somehow still see each other, let's imagine that they somehow project an image of themselves onto the other person's space plane. They immediately notice that there is a difference in age. The one who traveled at the speed of light did not advance so quickly through time as the other, who remained stationary and so is younger. But why do we find this model so compelling? Well, it is because of what those projections would look like during changes in direction. From the point of view of the first stick man, initially the projection of their friend seems fairly normal. However, as they start traveling very quickly in space, and their vector oriented in a direction away from time, a 2D shape reveals its inherent flatness. And from a face-on perspective, it goes from this to this. The speedily traveling stickman appears to flatten, with an effect that's more pronounced the faster they go, and the flattening takes place in the direction of their travel. The stickman who remains stationary might wonder at the strange change that is occurring to their friend, never comprehending that it represents a reorientation of a 2D figure in 3D space. Now, what captures my imagination about this is that this same thing happens in real life. According to Einstein's theories of relativity, objects traveling at great speeds in 3D space would appear from an external observer to flatten in the direction of their travel. This squishing effect happens exactly in line with this model, and is to do with time dilation. However, from the person who's traveling's perspective, they do not flatten, but it is the rest of the universe that warps. I talk about this in greater depth in another video of mine, where we can see the effects of spatial warping in a computer model. From their perspective, everything would stretch at the edges of their vision, while their destination would seem further away, which is again what this model would predict. The only difference is that in this model we're just exploring a 2D object stretching, so the stretch is only in one direction, while in real life it's 3D, which means it stretches in two directions instead. But that is what you might expect as you turn away from our conventional 3 dimensions and start orienting yourself away from time. But if this is correct, so what? Why does it matter? If time is truly a direction, then it deepens our understanding of the universe. It also raises more questions. What is the force that pushes us ever forward in time? Why does it seem that we can never move against it? Although in this model there is no reason why a vector could not point downwards, in real life that doesn't seem to ever happen. This model also answers the question of, if time is a direction, what is our shape in time? Does part of us protrude into the past or into the future? According to this model, that does not happen. We are flat pancakes in the fourth dimension, pennies that look round when you look at us head on, but revealing our thinness when we turn away from you. That's a strange thought, but it may just be true. This might explain why we are unable to see through time. We just don't extend enough in that direction for it to be visible. Your form might be quite different than you first thought. It's useful to consider the existence of other dimensions beyond the three that we see, but there are other edges to the frontiers in the universe that pose further questions. Is the universe inescapable? If we were to conquer the limitations of light speed and were to travel to space's furthest edge, what might we find? Just more space? Infinite planets and planetary systems? Or would we somehow come back to where we started? Amazingly, according to scientists, all of these are possible, but which one is correct comes down to the nature of that unseen world all around us. We need to understand the shape of space, and to do that, we need to begin by talking about infinity. You are likely already familiar with infinity. In maths, it is the concept of a number so large it cannot possibly be beaten. Of course, no such number exists. For any number you can name, I could come up with a number that is at least one larger than it. But in a way, that's sort of the point. In infinity, there is always another number. And when it comes to our universe, we have so far discovered no edges. There may always be another star or planet. An infinite universe is a little mind-boggling for us. We live in a very finite world with edges and endings. So the idea that there might be literally infinite more planets out there is a little bewildering. However, as we develop more and more powerful telescopes and push back the darkness further and further at the edges of what we can observe in our universe, all we are finding is that even the darkest patches of the night sky are turning out to be brimming with stars. So increasingly, an infinite universe might be something we are forced to contemplate. But that is not to say that just because the universe is infinite, there are not a finite number of things in it. That may sound a little counterintuitive, but let me show you what I mean. Believe it or not, there are different kinds of infinity when it comes to our universe. 3 possible scenarios could be true: a flat universe, a spherical one, or a hyperbolic universe. Allow me to explain. In a flat universe, if we were to form a grid to broadly represent reality, everything would seem fairly standard. All the lines would either be parallel to each other or perpendicular. An infinite universe of this variety would simply extend outwards in all directions forever and ever. This is a little boring, so I won't spend too much time on it. However, this is a lot like we perceive the universe to be. For the most part, all lines of direction appear straight to us. We can distinctly see the planets and stars around us, and we notice no real curving or warping. However, this is not the only way that the lines can be drawn. Consider for a moment a black hole. You may immediately notice the strange rings that appear to run around its equator, as well as across the top of it and along the bottom. This is something of an illusion. There are no rings across the top or bottom of this black hole. What you are seeing is the equatorial ring that's on the other side of the black hole. However, due to the powerful gravity of the black hole, the light that is hitting it is not bouncing off upwards or downwards into space. Instead, the rays are curving towards us as the black hole's gravity pulls them in. You are seeing the top and bottom of the ring at the same time. Light being bent by gravity. What do I mean by that? Actually, this is an excellent example of our second kind of universe. In a flat universe, all the lines that make up reality are fairly straight. But what if we were to come up with a rule? All the lines must instead curve towards each other. There is only one way such a universe could be drawn, and that is in a sphere. Consider trying to draw 2 parallel lines on a sphere. You might start off well, but will quickly realize that your task is impossible. All lines would converge towards each other, intersecting at least twice as they return back to where they started. What would a universe that was based on these kind of lines look like? Essentially, rather than going in the straight line you thought you were going in, you actually would be traveling in a massive curve. It's a bit like those computer games where you travel off one end of the screen only to reappear from the other side. In a spherical universe, you could travel infinitely, but ultimately you would only end up arriving back where you started. With a powerful enough telescope, and if light were to travel a whole lot faster all of a sudden, it would be possible to look at the back of your own head. This kind of universe contains a finite amount of things, but it appears infinite because you just keep bumping into the same things infinite times. Thanks to objects like black holes and powerful stars, we do indeed have evidence that our reality sometimes is a curved, spherical one, at least near large bodies of mass. The inside of a black hole's event horizon is this kind of infinite space. No matter what path you take, you can never get out of it. However, let's consider our last example, the hyperbolic universe. This one is the hardest to visualize, but the idea is simple. Instead of having all lines remain parallel or move towards each other, every line must move away from everything. Drawing this is inherently tricky because everything keeps getting wider exponentially. The only way you can do that is to either buckle your nice flat disc until it becomes something like this, or warp what you are seeing like this. All of the objects in this image are squares. However, they are squares that are obeying our rule that all their lines must be diverging away from each other. This leads to the very strange situation where you can have 5 squares all meeting up at a corner instead of the usual 3 that is possible in normal 2D space. Alright, this seems a little confusing. What does it mean if space is hyperbolic? Well, let's consider what it is we are curving around. You might have noticed when we talked about our spherical shape that there must be something we are curving around. That direction of curvature is in regards to time. Imagine, if you will, a series of timelines. We go a little more in depth with the interplay between space and time in my last video, which I would really recommend you check out. But for now, just remember for this model that objects in time move forward along their timelines in the direction of up, or the future. If they move left or right, they are moving through space, getting closer to each other. If we introduce a large mass into this model, it warps the timelines. Now, if you were a small object traveling along one of those arrows that got too close to the mass, suddenly your path of travel no longer goes directly up towards the future. It pulls you left or right towards the mass. There are several reasons for this, but the essential thing to recognize here is that now your straight path towards the future pulls you in towards the planet, so you'll have to accelerate away from it just to stay on a straight path. In a nutshell, you are experiencing gravitational pull. Even the planet is affected by this. The atoms on either side of it are squeezed towards the center of mass, as if it were being forced down a narrow tube by giant invisible hands. Let's get back to hyperbolic space. In this model, the opposite thing is happening. All lines are moving away from each other. We could represent this by curving space and letting our timelines be straight, which is nice because it captures the idea that from your perspective, your time is always ticking forward normally. But let's warp this slightly so that space is flat. It's all a matter of perspective after all. Here, parallel lines are also impossible, but this time, rather than converging, all parallel lines diverge more and more. Everything moves further and further apart. Why does that sound familiar? It is because that is what the universe is doing. This is not noticeable within a galaxy, where there is enough mass and gravity to keep everything together. However, from what we can see of the universe as a whole, every galaxy is moving away from every other galaxy. Scientists try to explain that with dark energy, but maybe all that is happening is that the universe is just naturally hyperbolic in its shape. So what would that mean if the universe really was hyperbolic? It would mean that the universe was really infinite. The flat space we looked at was infinite. For each light year you traveled out, you discover another light year's worth of space. However, with hyperbolic space, you discover more than another light year's worth of space. It's like opening infinite doors, except inside each door are two new ones. The possibilities would be far more endless, far more infinite than in just regular flat space models. But also, it means that given enough time, the rest of the universe would drift away from us until our galaxy was all that was left. Scientists have looked across the universe, however, have not noticed this hyperbolic space in action. In fact, things all look pretty flat, so perhaps flat space is the correct answer. Yet, this still leaves room to me for hyperbolic space to be the default. After all, if matter is curving space towards it, and the universe appears flat, it would make sense that the universe was curved in the inverse, at least to some degree. Perhaps all three models are true. Perhaps the universe is by default hyperbolic, but mass brings it together in such a way that it perfectly offsets the inverse curves of the universe to the point where everything appears flat. There certainly seems to be some evidence that this is the case, but it's very difficult to know for sure. Which model do you think is correct? Or maybe you feel that we do not live in an infinite universe at all? Please leave a comment down below to tell me what you think. But for now, just remember, the unseen world might be a lot more influential on our universe than we are currently aware of. Why does reality have a speed limit? It is common knowledge that the speed of light is the fastest that anyone can go, but why does this cap on causality exist? And why is it exactly 299,792,458 meters per second? Why not more? Why not less? If you're like me, you've wondered about these strange properties of light, but recently I think I might have found an answer, and it lies in hyperbolic geometry. And the more I've considered it, the more it's blown my mind. Let's talk a little bit about light. There is an interesting observation we can make about light. From an external perspective, it appears as if light is traveling at 299,792,458 meters per second. This is true no matter what perspective you look at it from, whether you are at standstill, whether you are moving towards it or away from it. It always looks as if it is traveling at this speed. However, there is a single, interesting exception to this rule which had always puzzled me: the photon's perspective. Einstein has proven that for an object traveling at light speed, time would slow down so much that it would be at zero. If you were to suddenly start traveling at the speed of light towards Jupiter, you would notice zero time passing, but would observe that you have traveled 679 million kilometers. And then would promptly die of the lack of air, the punishing g-forces, and the friction burn along the way. But what happens if we try to calculate your speed using these figures? Well, speed is distance over time, so 679 million divided by 0 equals... If you tried plugging this into your calculator, you would quickly run into an error here. Calculators do not like dividing by 0. This is because the smaller the denominator becomes on a fraction, the larger the total number becomes. If you reduce the value of the denominator all the way down to 0, the only way this can work is if your total answer becomes infinity. If you travel for 0 time over any distance greater than 0, you have just traveled at infinite speed. So from light's perspective, it is traveling infinitely fast, not at 299,792,458 meters per second. Let's call that c from now on. So why is it that everyone else detects light traveling at c, but light thinks it's going infinitely fast? What I am about to share is one possible theory. It's going to incorporate the 4D space we talked about when considering the nature of time, as well as the hyperbolic universal geometry we discussed for the shape of space models. Both models were important building blocks that we can now build upon in a single 4D hyperbolic geometry. This may sound intimidating, but it's the same as the 4D space we've worked in before. Let's compress all of 3D space down into a single 2D plane. This leaves us the final dimension free to be made into the time direction we looked at earlier. For the hyperbolic element, all that means is that in our space, all the lines diverge away from one another, always. This has the effect of warping space in a way our brains don't really process well, but essentially means there's more and more space the further out you go, but exponentially so. Other than that, traveling through this space obeys the same rules that traveling through 3D space uses in terms of the physics rules involved. Objects that start moving must be acted upon by another force or they will continue moving at the same rate. Objects at rest remain at rest. Conservation of momentum is maintained. Now let's imagine for whatever reason there was some big expansion event in the past that sent us all moving in the upwards direction. A big bang, if you will. I wonder where one of those might have come from. But this expansion was not simply in space, but in time too. It's a 4D explosion. We are now in motion, moving solely up at the top of this expanding bubble. For now, we are not moving anywhere in space, we are simply moving forwards in time. We travel consistently, and will continue to travel consistently until we are acted upon by another object or force. But as we are new, and there is nothing but empty space above us, we are going to go up infinitely. There's nothing up there to bump into. Now, let's imagine for a second that we decide we no longer want to go straight up. Let's try to change direction. In physics, any change of direction is a form of acceleration. This may not make much sense intuitively, but it becomes easier to understand if we split our vector into two components: our velocity in the x direction and our velocity in the y direction. It then becomes easy to see that changing our direction comes about by decelerating with one of our values and accelerating with the other. We don't have to change both values though. Let's just give ourselves a little impetus in the x direction. Obviously, the more we are pushed, the faster we are going to travel, and the more our total vector begins to lean towards a perfect horizontal line. The size of our vector increases. However, let's say that we want to go faster. In fact, we want to go so fast that we are no longer traveling in the y direction and are only moving in the x direction, or space. Is there any amount of push we can get in the x direction that will make it so that we are actually going completely horizontally? No. You could increase the distance in x by a larger and larger amount, but as long as y has some value, you will never actually get that vector perfectly going across space. The only way you could get your vector in the time direction to slow down is if you pushed against something that's ahead of you, or pulled on something behind you. But if everything near you is in the same second you are in, there's nothing to push against. You can only push each other left or right. Nothing is ahead or behind. Interestingly, with only this available to you, your vector can trend closer and closer to flat, but it never actually reaches it. And increasing your speed produces diminishing returns on how much flatter you can get your vector. You have a limit. You would essentially need to go infinite speed to approximate a flat line, and to go infinite speed, you would need infinite energy. Difficult to get your hands on. Of course, this is where the idea diverges from reality. There's nothing here so far that imposes a speed limit on our model. You should easily be able to go faster than the usual light speed limit. With infinite energy, you could go 3 billion meters per second, or 3 trillion. But in the real universe, we don't see that. Everything normally seems to be capped at c. There is a similar trend where the more energy you put in, the less additional speed you get, but that occurs at close to light speed, not infinite speed. So our 4D model seems to have failed. But this is not regular 4D space. This is a hyperbolic 4D space. Let's observe what happens when you try to travel at near infinite speeds when the lines start to bend. Here you have zoomed along at a speed that's as fast as infinite as you can imagine. Speed is a tricky little concept here, but let's say that from your perspective you covered a distance of 400 million meters in a second. So faster than the speed of light. What happens? Well, you hit this little curved line over here. Although it is bent to be almost a C shape, if you follow the line down, you will see that it is a timeline, not a space line. And because it is a hyperbolic space, there is more here than meets the eye. Let's jump over to that point and see where we ended up. Although in our movement vector, by our origin we only traveled one square high, by our end destination we have ended up at a point multiple squares high. By taking a journey sideways, and by only experiencing a second of forward momentum through time ourselves, we have ended up many seconds into the future. We have taken a shortcut into the future. This is what we observe in the real world. Objects that move at great speed seem to suddenly experience reduced time. They believe only a few seconds have passed, but far more time can occur to an external observer. And suddenly it really throws off our maths. Because how does an external observer record our speed? If we started at an origin point of 0, but ended at an origin point that's 10 seconds into the future, they have to say that we have traveled 400 million meters in 10 seconds for a speed of 40 million meters per second, far below the speed of light, no matter what we thought we were doing. Which is kind of like what light seems to be experiencing. And the faster you push yourself in the x direction, the more you encounter the warping effects of hyperbolic geometry, and the more it keeps pulling you back towards the speed limit cap of the universe. It will never let you exceed it. This explains why there is a cap to the universe. Not even light, which as far as it is concerned does travel infinitely quickly, would be able to overcome it, provided the base we were resting on was ever so slightly curved. As soon as the photon slid onto the plane that was space, it would get swept up in the curvature of this hyperbolic 4D space. It would trace the limit of it, true, but it would get caught in it. And then, from our perspective, it would start to look as if we were simply moving uniformly at a speed of c. After all, we would see it leave, and then we would time how long it would take to arrive at its destination. It doesn't matter for us that it believed that it arrived there instantaneously by taking a shortcut through time. We would just record it as having arrived after some time had passed. So there you have it. Why is there a speed limit for our universe? Perhaps because space is curved and our 4D space is hyperbolic. At least, so claims this theory. It is, it must be stressed, just a theory. It's possible that smarter people than me in the comments will explain to me why this is wrong, and it doesn't entirely account for the role of gravity in distorting this 4D space. However, it does neatly highlight why light physically can't travel faster than it does. The faster it moves, the more serious the drag placed upon it by the hyperbolic geometry it encounters, which I find quite appealing. In fairness, it would be intriguing to see if from our perspective we could travel faster than the speed of light. This model claims it is allowable, but we have never gotten close to that speed, so it would be difficult to test it. The fastest a human has ever gone is 11,083 meters per second, when NASA astronauts returned in a spaceship from the moon. It would require incredible amounts of energy to travel c from our perspective. If it is true though, it would provide firm evidence that our universe really was hyperbolic in nature, and sadly quash any hope of us traveling backwards in time at any point. So, sorry time travel fans. But at least we can console ourselves that although we probably can't travel to the past, traveling through shortcuts to the future is definitely within the realms of possibility. So there you have it. The universe is a strange place filled with features that we can't entirely account for with our intuition. However, with the right models, everything becomes a little easier to conceptualize. Time and space are no longer quite so mysterious. Of course, as time goes on, we will likely encounter new, strange phenomena that will force us to reconsider our models, but in so doing, we get nearer and nearer to what is really going on. Through theorizing and developing our theories based on new information, we will one day create a model that accounts for everything. Until then, hopefully the models we've discussed today will have given you some things to think about. It's incredible to me that although much of the universe around us cannot be directly seen, it's possible to explore it. But that is the beauty of the unseen world. Although we cannot see it, we can detect its influence on our day-to-day lives. It shapes the motion of our day as we pass from the present into the future. It lays out the cause and effect happening one after the other, but never the effect happening before the cause. It bounds the universe and gives us the scope of what we have to work with. The reasons for this happening are sometimes mysterious and baffling, but our logic allows us to catch glimpses of the truth that underpins it. It just takes us stopping occasionally and asking the most important question of all: why? Thanks for watching. If you enjoyed this supercut, be sure to check out my others in this playlist here. And a big thanks to my patrons and members. If you want your name added to this list too, plus a bunch of other perks, you can support the channel using the links in the description. Also, join me on Discord. All the best, and see you next time.